Okay, so differential equations, what's it all about, right? What's the big deal? So the game is really literally this, and it will always be this, okay? Frequently, you don't have a how much stuff do I have meter, okay? What you have oftentimes is a meter that talks about, for instance, things like miles per hour, okay? Or you have something that has to do with it'll be an ammeter, right? But what is that really? Well, an amp, I can't spell today. An amp, whatever. Switch those two. Anyway, the idea is, what is an amp? Well, an amp is a coulomb per second. In other words, it's an amount of charge, right? And these are the things that you're going to see frequently when we're dealing with, just in life in general. We're going to see rates of change, not so much, what do we have here over time. So if you let things go on, you will have accrued miles, okay? Over here, you will have accrued charge or coulombs, yeah? Over time, that's how much you'll have accrued. Well, what we'll end up starting with is for instance, a dx dt, okay? And in the case of a nice linear function, let's say you're just driving 60 miles an hour, this is very hard to say, for instance, well, geez, Jay, could you give me an equation that tells me how far I've gone? Yeah, 60t, boom. Well, how'd you do that, Jay? Well, I integrated both sides with respect to t. Boom, done, piece of cake. That's right. And then a nice easy one, there it is. And isn't that swell? And then, well, where am I at time equals 2 hours? Well, I don't know. It would kind of depend on where you started. In other words, there'd be plus a constant. Remember that? We always had a plus c on the end of those guys. So this plus c is frequently going to be, although not always, so don't take it to the bank on this. There's a few instances, for instance, in the case of an exponential equation, that c won't always be the value at 0. So just be careful. But typically, it's the idea of, where were we? In other words, it won't always be x of 0, but it will be based on at least x of 0 or x of 1 or something. In other words, you have to know how much I have now. I had to know how much I started with. Does that make sense? At time equals some arbitrary value. Typically 0, but not always 0. Okay? And in a similar case over here on a charge deal, I think it's pretty straightforward. Oftentimes you're building charge on a capacitor or in a situation like that. Obviously there's going to be exponential functions because they can only develop a certain amount before it's full, if you will. So things are going to change. It won't be a nice linear perfect function. What would be nice though is this. We're going to start off with, and typically it's going to be x as a function of t or y as a function of t. We assume that our x or y is a function of t almost always, okay? And so we will be given something like this. We'll be given dx dt is equal to blah, okay? And the idea with that is that that's great. This is the rate of change. Why does it say dx dt, stupid? There you go. Or maybe it's dy dt. And the idea here is that our x's and y's are both quote-unquote y's, if you will, and t is our x value in this case. Does that make sense? In other words, t is our independent variable, and x or y, whichever it happens to be in this case, will be our dependent variable. What I would like to know is this. I'd like you to turn this thing inside out. Let's say it was something very easy like 3t plus 5. Okay? What I'd like you to do is we'd like to solve this for x as a function of t is equal to a function. But that's not the end game. The end game is to then say, well, listen, at x of 7, for instance, maybe, how much stuff should I have? How much stuff should I have? Okay? And that's the game, is always to use it to predict for something. This isn't always possible. And why is that, Jay? Well, because sometimes, as you know, there isn't always, because to get from here to here, you're going to have to be doing an integrate. Sometimes you can't always integrate everything, is that right? So a lot of times there's this functions you can't integrate. They don't have an integral in closed form. And so sometimes we won't be able to find this, but we can integrate from, let's say, 0 to, let's say in this case, 7. Using a numerical approximation, we should be able to find out how much stuff we've accrued in that amount of time, okay? And then you can just add on to whatever amount you started with, okay? So it's at x equals 0, you had time equals 0, you had this much stuff. So between 0 and 7, that integral will give you how much more stuff that you've got. And so then when you add them together, voila, there you go. Okay? That will always be the game as we're playing these guys. Always, 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 always. Okay, so again, some will be very straightforward. Some will be really hard. Some will be darn near impossible. As a result, we will teach you some solutions to some easy ones. For instance, this guy right here. Suppose you had this guy is equal to 0.05x. Now, this should look weird. The derivative is equal to 0.05 times the original function. Dude, that's weird. I remember the first time I saw that, it creeped me out. But let's think about this for a minute. In other words, what you're saying is, what derivative is basically equal to its derivative? Or what derivative is basically equal to its original function? Of course, it's e to some power. Does that make sense? It's e to some power. We just don't know what that power is, in other words. Does that make sense? We don't know what it is. So if you think about this, this is what we're going to be doing on problems like this. This one happens to be a very straightforward problem. Typically, the way we show it is to do this. But we'll get into this more and more as we go along. There you go. And we will what's called separate. Separate. Because this is what we call a separable differential equation. We'll talk more about that as we go on. If you integrate this side with respect to t, or sorry, with this side with respect to x, you're going to get ln of x. Normally, a guy would put plus c here, but we're not going to do it. And on this side, we're going to have 0.05 t plus c. In other words, there's a c here, and there's a c here, but a c plus a c is a c, yes? So I can move all the c's to one side. Now I don't want the ln of x for crying out loud, so I'm going to exponentiate on both sides. When I do that, I'm going to get x is equal to, I'm going to have e to the 0.05 t plus, oh, for the love of George. One moment, please. Oh, excellent. 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 Press enter and we'll try to fix it. It's not fixed. Oh, there it is. Good. Cool. Okay, well, let's try to exponentiate again, shall we? Oh, you go away. No one likes you. There we go. Okay. So you get x equals, and you have e to the 0.05 t plus c, which of course could be rewritten as e to the 0.05 t times e to the c. But e to a constant is just it's just a constant. So we'd have x is equal to c e to the 0.05 t. So in this case, as you can see, we can solve for x as a function of time. Now, what is c going to be? Well, I don't know. You'd have to tell me something. So maybe if I told you that x equals 0 was 100, well, then if you would plug in the 0 here, you 0.05 times 0 is 0. E to the 0 is 1. So you'd end up with 100 is equal to c. And so, of course, you'd end up with this guy. Okay, now, of course, where does this one come into place? Well, populations. It's huge. It's huge for populations. It's pretty straightforward kind of a deal. There's a zillion other examples. We'll go through a lot more of them as we get there. This is a very simple population, but a population is kind of make-believe in that it never tapers off. In reality, most of our populations will start off here. They'll grow like a weed initially, then they'll kind of taper off. This is called logistic growth. We'll see this as well. How many fish can be supported in a pond. What happens if you put too many fish in? They would die, and they would come down to this carrying capacity. Okay? What happens if you start with too few fish or whatever? Well, if you can't have negative in this case, but whatever. What if you overfished it? You could fish it out. These are the kind of things that we'll be looking at. There's a zillion of them. Okay? So I'm not totally going to get into them in this case. But what you're going to start to see is that some of them are, you're like, oh, when you look at it, you're like, oh, that's going to be exponential. Ooh, that's logarithmic. Ooh, that's this, that's this, that's this. And you're going to be able to start to recognize them as we go along. Okay? We will run into, from time to time, what are called, oops, I should have mentioned this previously. The one we just did a minute ago, dy dt equals 0.05 t. It was separable. It's also a first order because dy dt is a first derivative. We'll run into second orders. Or whatever. Maybe let's just make it equal 0. That would make my life easier. Equal 0. Cool. And this is a second order. We'll get into that more later, but second order because second derivative. Turns out second order it's linear. We'll talk more about why that is later on. This one's also what's called homogeneous. because it equals 0. So in other words, once you establish what kind you've got, then you can establish then, okay, well, how am I going to attack this one? Okay. So what's going to happen again, I'm going to hold you to this, is in this scenario, we're going to be looking at some models that have been developed, of course, as I say. This is one that very clearly describes populations. It also describes human growth. It's called logistic growth. We'll look at that. We'll talk about why that comes about. Well, we've seen it in nature, and we've come up with a mathematical formula to describe it. That's where it came from. We'll talk about some stuff when it comes to some, we'll talk a little bit about some chemistry, reactions, talk about some of that. Obviously, different reactions happen at different rates. Over time, they will slow down as time goes on, oftentimes because they run out of poop. They run out of stuff that there is to convert. For instance, the place where this comes up to my mind the most is I used to make moonshine every year in my physics class at the high school that we'd run an engine on. And the rate at which those reactions took place changes over time. Over time, the sugar content goes down, therefore the rate of the reaction goes down. And you make alcohol at a slower rate at that point. Okay, just things of that nature kind of come into play. In section 1.1, what they're going to do is give you some equations, not unlike this guy, perhaps. Oh, that's too much work. I don't want to do that. This one here, yes, no, yes. Sure, let's do that one. So y double prime plus 4y prime plus 4y equals 0. Now later on, we'll know how to solve this right off the bat. But you're like, I don't know how to solve it right now. That's cool. So we are going to give you a couple of suggested solutions. Now this one is going to come back later on. We're going to see this same problem come up later on. You're going to be like, I remember when we did that. That's cool. Now, the idea is these are suggested solutions. They want you to show that, in fact, they are solutions. Well, to do that, obviously, I can plug y1 in place of y, obviously. But to plug this in, I need to know the derivative. So let's try this. And then, of course, I need y double prime as well. Excuse me. And so if you plug those in, you will get 4e to the negative 2x. Plus, it's going to be minus 8, you moron. Minus 8 e to the negative 2x. Plus 4 e to the negative 2x. Does it equal 0? It sure does. Check. This is a solution. Cool. What about this fellow? I don't know. Let's find out. You're like, I don't remember how to take the derivative of this. Well, it's power rule. Or not power rule. It's product rule, you dummy. But if you don't remember, by all means, use your calculator for this. I won't mock you too hard, probably. There you go. There's our first derivative. I'm going to jot that down. So I'm going to write it down as the actual thing. So it's going to be e to the negative 2x minus 2x e to the negative 2x. And then I'm going to do the second derivative. And just get in here and give it the old comma 2 routine. So I'm going to get 4x. Oh, fart. 4x. And minus 4. Now, if you go through and plug it in over here, the recipe says to take y double prime. So 4x e to the negative 2x. Plus 4 times the first derivative. So plus 4 e to the negative 2x. Minus 4 times 2 is 8x e to the negative 2x. Plus y, which is x, e to the, or 4 times that, sorry, e to the negative 2x. And the question is, does it equal 0? That's the question. I don't know. Here's 4x, here's negative 8x. Those guys cancel out, those guys cancel out. Check, it equals 0. Ergo, this is a solution. Now, again, this initially is just showing you, hey, there could be more than one solution to a problem. Is that because, Jay, it's a second order? And second order, I mean, it feels like it almost looks like, geez, this almost looks like x squared plus 4x plus 4. And is that because there's two solutions on a quadratic? Yes, but don't tell anyone yet. Yeah, exactly. And if it was a third order, would there be 3 solutions? See. So if it's a first order, only one answer. That's right. That's right. And so that's the kind of things we'll be looking at. You'll be doing some testing. You'll be saying, here's a proposed solution. What do you think? You'll also be given one or two like this and just see what happens here. So for instance, and the reason they give you this one is to make you think a little bit. And this is exactly why I want you to know this. So this one here comes along. And they want you to solve it, but they want you to know that y is of the form e to the rx. Well, that's cool. Well, the recipe says this. Well, the recipe says then I would need to, let's just do this, take the derivative, and I would get r e to the rx, and I believe that y double prime is r squared e to the rx. Oh my goodness, if you evaluate this, you will get r squared e to the rx equals e to the rx, and you're like, wait, this is weird. Let's put them on the same side. Wait, is it true, Jay, that you could factor those out? Well, of course. Is it furthermore true that this can never equal 0? That's true. So I don't need to worry about that. That's right. So the only thing that's going to make this 0 is this. That's right. Wait, isn't that r plus 1 and r minus 1? That's right. So 1 and negative 1 would be my two answers? That's right. Wait a minute. So you're saying that if I took e to the x or e to the negative x, they will both work. That is exactly what I am saying, sir, ma'am. And if you plug those in, you will get, boom, what are you going to get here? You are going to get, oh, I dropped my 4. That's funny. Where did my 4 go? What a dummy. Let's try that again. I believe they should be 0.5s. Boom. Is this going to be 2r and 2r? Well, I should do it this way. That's just easier. 2r plus 1, 2r minus 1. But they're halves is what I'm getting at. There we go, you big dope. All right, let's try it again, Jay, you goober. Oops, that's a quarter, that's an eighth. All right. That's a quarter, that's an eighth. Judas Priest. And these should be to the 1/2 and the 1/2 and the 1/2. Good night, nurse. Half, 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 and not that. Oh, let's try this again. See if Jay can actually do it right this time. What do you think about that? By the way, if I had done it the way I was going, I would have screwed it up. Okay, because what I would have ended up with is 4e whatever does not equal 1e. Does that make sense? And because it's not equal, well, then it can't be correct. Does that make sense? They has to make the solution, the equation, equal. And that's how I knew it was a problem. That's why I stopped. And because I knew I had a boo-boo somewhere. So that's another thing I really like about, well, I've always liked that about all math, as I normally know when I leave the classroom whether I was right or wrong. Now, I might have been really bad on the test, but at least I know I'm bad on the test. Unlike, you know, if you're a person who's taking a poetry test and the poetry is clearly about motorcycles, but and you say it's about motorcycles, but no, it's about the love life of an ant or something. That's ludicrous. If you take this right here and stick it into here, you're going to get 4 times a quarter is 1 e to the half x equals e to the half x. Yay! If you put this guy into here, again, 4 times a quarter is 1, and again, it matches up. We'll be doing this a lot as we go along. This the idea that y is equal to e to the rx, and then y prime is r e to the rx, and y double prime is r squared e to the rx. We'll do that a lot on pretty much every single second order or higher differential equation. First orders, we have better ways of attacking them than that. Okay? And so we'll be messing with that as we go along. You'll see how that works. It's a pretty sweet deal. In section 2, it's all about some very specific ones. And so I'm going to do some examples of them here. So the initial ones are pretty straightforward. It's all about acceleration and displacement and velocity and so forth. And so, for instance, number 14 here, the acceleration is a function of time is equal to 2t plus 1. Now, that's creepy. Your acceleration is picking up steam as you go along. Okay, that's crazy. So what's going to happen here? Well, we're going to have some very interesting things happening. But in order for this to happen, okay, I need to know how fast I was going initially. In order to solve this, because remember, this is equal to dv dt, okay? And so if you did that, you're going to say dv dt is equal to 2t plus 1. And this is separable. That is, I can leave the t's on one side and have v's on the other. So dv would equal 2t plus 1 dt. Integrate. What's the integral of dv? It's v. What's the integral of this side? It is t squared plus t plus a constant. Well, what is the constant, Jay? Well, I don't know. I feel like you put zeros here and here, you get 0. You get c is equal to -7. Beautiful. Now, here's a question for you. What is velocity? Well, velocity is the change in displacement over time, which means this was the second derivative. Right? Second derivative. Or if you prefer, x double prime. So to do this, to solve for x, obviously I'm going to need an x naught as well, yes? And so x naught, in this particular case, they gave us was 4. So can I still do this problem? Sure. dx dt is equal to t squared plus t minus 7. Again, it's separable. That is, I can separate my t's and my x's. We'll talk more about that in the future in terms of the exact definition of that. Okay. When you plug zeros in for your t's, you will find that x equals, or 4 equals c. Yay. And there we have it. And then at some point they may ask you, well, where are you? So I could ask this question, where are you at t equals 4? I don't know. Let's find out. You plug that baby into here, you're going to get x of 4 is equal to 64 thirds, whatever that is, plus 16 over 2 is 8. Minus 28 plus 4. Need a calculator for that. .333. You are at 5.333. Cool. Okay. And that's kind of how that's going to work. Okay. Yeah, we can do a couple other ones here. Okay, there you go. Cool. So a car traveling at 66 miles an hour skids 176 feet after its brakes are applied. Under the assumption the braking system provides constant deceleration. What is that deceleration? For how long does the skid continue? Okay. So in other words, we're going to write down what we know. So initial velocity, or v of 0, or if you prefer v of 0, is equal to 88 feet per second. Now you could do it miles per hour, but it's kind of annoying because you get like 0.00001 hours for this and thing. And it's kind of, when you skidded 0.0005 miles or something, it's kind of weird. Okay, they skid 176 feet, 176 foot skid. Okay, that's cool. I want to know how long did it take? How long did it take? And we are assuming constant deceleration, which is probably a poor assumption, but that's what we've been asked to do. Okay, so let's think about this for a minute. So dx dt, or not dx dt, dv dt is equal to a constant. That makes sense? And let's call it k just for fun, shall we? Okay, that's what we were told. It's equal to k. Cool. All right. Okay, well, I don't know what I'm going to do with that yet. So let's hold that thought for a minute. Actually, I do know what I'm going to do with that. Let's do this. Let's do dv is equal to k dt. Let's integrate. I'm going to get v is equal to kt plus some constant. Cool. What is that constant? Well, that constant right here is what? Well, it's 88. So v is equal, how do I know that? Because at 0, this goes away, yes? So kt plus 88. That make sense? Now, I could at this juncture tell you how long it took to do this, because what do I know? When I come to a skid, the end of my skid, how fast am I going? Well, I'm not. You see that? So I get kt is equal to 88. Ooh, no, I'm sorry, plus 88. So I get kt is equal to negative 88. So t is equal to negative 88 over k. And you're like, well, that's not helpful. No, you're right. It's not helpful until I find k. Remember, this is then, of course, dx dt, correct? Well, let's do this. So if I do dx dt is equal to kt, oops, kt, you idiot, plus 88, and I, again, separate, dt, x equals kt squared plus 88t plus a constant. Are you with me? Some constant. And so, well, let's think about this for a second. Okay, cool. Where do you want us to be at t equals 0? Well, I want us to be at t equals 0. I would like us to be at 0, was define where I start from 0, which means this c here is 0. So I'll look at this guy. Nice. Now, here's what I know. At some time, I have skidded 176 feet. Does that make sense? And so the question is, when does that time happen? Oops, there's a t. kt squared, stupid. There you go. Now you're like, well, how am I going to solve this? You know, is there a better and a worse way to solve it? Yeah, it's a good way to solve it right here. Right there is your way to do it. So you're going to get 176 is equal to k, which is, now I could do it 2 ways. I could solve for t, which is what I did over here, or I could solve for k. How about that, huh? I think I want to solve for k. So if I solved for k, I would get negative 88 over t. Does that make sense? So negative 88 over t times t squared plus 88t. And, oh, I might have made a little boo-boo here. Let me pause. I made a little boo-boo. Yeah, sorry, it took me a little longer. I had to go back, and I was looking at it from a physics standpoint, and I forgot when I integrated here. Got my 1/2. That was what was killing me. Freaking idiot. Let's try it again, Jay. Woo! Okay, great. So let's substitute, shall we? Okay, it's 1/2 k. And then your t is going to be 88 over k squared plus 88 times 88 over k, negative this time because it matters because I'm not squaring it that time. Okay? See if we can do this right this time, you big dope. Goodness sakes. All right, so it's going to be over k. You see that? It's going to be over 2k, I guess. 88 squared. Believe. Minus, well, I can't do math in my head. No, I don't care anymore. Let's do this. Oops, well, let's do this. Shall we clean it up? 88 squared. Let's go ahead and do that. Let's go ahead and just square it. Whatever. 7744. And then, of course, wait, that's the same thing, isn't it? 7744 over k. Cool. So, yeah, let's divide this out. And you're going to get 77 divided by 2 is 3872. 3872 over k. Cool, since they're all both over k, we can subtract, and you're going to get negative 3872 over k is equal to 176. I like so. And then you will find that k is equal to so negative 1 over 22 is equal to k. Like, that's nice. Well, what does that tell us then? Something just went screwy there. K is, Oh, just a dadgum minute. It should be positive. Oh, no, there it is. God, I can't subtract. Look at this, people. You multiply by k, you divide by 176. It's negative 22. That's what it's supposed to be. How about that? So then if you plug it in, negative 88 divided by negative 22, you could take 4 seconds to do the job. Yay! Holy mackerel, I can do math, but boy, howdy, I don't know. Crazy talk, dude. Okay? Yeah. Cool. So, yeah. I'm going to sketch one of these out, too, just for a good time. So this is a velocity function. And I just want you to think about this a little bit. It looks like so. This is where this is time. This is velocity. And then it's like so. And then it's down to here. Like so. Okay. What I'd like to see is I'd like to see x as a function of t. Okay, that's what I'd like to see. Well, what's happening here? Well, if you look at this is linear. Okay, so a linear function or a line is a derivative of a quadratic. Does that make sense? Yeah, sure, of course. And so what is this line? Well, one can see it. This is easily, well, I'll write it as x equals 5/3 t. That's not x equals, that's v equals. You see that? That's v equals. So then if I integrate that, you're going to get x equals 5/3 t squared over 2, or in other words, 5/6t squared, plus some constant. What is the constant? Well, the constant is 0, because that's where it started. Okay? So what I'm going to do, and I love my Desmos.com. Let me pause you for a sec. Here we are. So what I'm going to do is I'm going to graph this guy. I'm going to graph it in pieces. And I'm going to graph it. It's going to be, what did I say, 5/6. Go away. No one likes you. Oh, for God's sakes. Stop it. 5/6 x squared. You have to do it with that, and you have to use x in this deal. Okay, now I'm just going to get pissed off here in about a minute. Where x is between 0, x, and what do we say, 3? Correct. Okay, so that's the first piece of it. And then what happens? Okay, well, then you get this middle portion. Well, the middle portion is the constant. Okay, so that means because this is a constant velocity, our displacement function will be linear. Well, right now it's it's v equals 5. So if you integrate that, of course, you get 5t. So you're going to get x equals 5t plus a constant. Well, what constant? Well, we were at 5 initially, so 5t plus 5. Here's what you're thinking. That's what you're thinking, but you'd be wrong. Because remember, it isn't x of 0 equals 5. It's x of 3 equals 5. Does that make sense? And so if you did this, you'd have 5 equals, then 3 times 5 is 15. You'd have c is equal to negative 10. And so you're going to go 5x minus 10, bracket, and you're going to go 3 less than x less than 7. And I made a little boober there, didn't I? You see what happened, friends? They should match up right there. Oh, there's my problem. I used, like an idiot, I used the initial what? I used the initial, I used the initial velocity, not the initial displacement. It should have been 7.5. So it should have been 7.5. 7.5. So negative 7.5. And so what this should do is it should be a nice, smooth function. And I know that because, well, it just makes sense. I can't jump from place to place as all of a sudden I'm driving along. So there it is. Nice. Now notice where we start this time. At t equals 7, we are at where? 27.45, which is just bizarre. But I want to write that down. So x of 7 is 27.45. And then what do I have? Well, this is a negative slope over here. I go negative 5/3. It is the mirror image of the other side. So then I would have x equals negative 5/6 t squared plus a constant. What would that constant be? Well, that constant would be this guy when t is equal to 7. Now, a couple ways to do that. Sometimes, and I'll probably show it to you later, not right now. Sometimes I would do it where I would just do a translation, basically, of the function. It's the same function, it's just been translated over, and that's how I would attack it. I don't think I want to do it this time. So, not minus plus, you dummy. Plus 5 divided by 6 times 49. So it's going to be 68.2833333. 68.23 minus 5/6 x. Something went wrong there. 68.23333. Okay, what did I do wrong this time? So somewhere up here, I should see my line. You see that? So I made a little boober there. I made a little boo-boo. Little boo-boo. So let's come back and see where J did wrong. You see it should be here at 27.45. And it's way in the Sam Hill up here, so that's obviously incorrect. So let's see mathematically what I did wrong. Oh, what a dummy. Okay, friends, this, as you can see, this is not linear. This is not linear, but if you notice when I typed it in, I forgot my x squared. What an idiot. Oh, I can do math. Oh, I was worried for a minute. Judas Priest. 7 less than x less than 10. Kaboom! And that, my friends, that right there, my friends, is my displacement equation. Right there. Okay? Displacement, what does it mean? What does it tell me? It tells me this is just what's happening here, and you know, obviously the stuff above the x-axis, I'm in front of the starting position. The negatives means I'm behind the starting position. Again, in the real world, you can't turn on a dime like this, so that's kind of weird. Okay, that'd be a problem. What's the derivative there? It's 0. You have a variety of issues there in that particular case, but we're just gonna pretend we didn't see that. Okay, it's a problem that your book has, but that's how I would draw this problem out. I would use Desmos to help me draw it. I just think it makes it look better and easier for me. Sometimes. Not always, though. Okay. That is, in essence, section 1 and 2. It's going to be mostly just getting the grasp of these things, looking it over, getting comfortable with it, doing some examples that are very straightforward, going back to your physics days, and things like that. So none of them are going to be terribly difficult. I think you'll find them to be pretty straightforward.